Hello everyone and welcome to the video series of cross-chain development using the Xcan platform. I am excited to guide you through the cross-chain development and Xcan platform over the next few minutes. In this tutorial, we will walk through all the chapters of the platform. I will explain what you will learn in each chapter, show you the key concept and demonstrate the actual Xcan platform interface so you can see exactly what your learning journey will look like. So let's dive right in and explore more about the cross-chain. Let me start by painting a picture for you. Imagine you are living in a world where every city has its own currency that only works within that city's boundaries. If you want to travel from New York to London, you can't just take your dollars with you and use them there. You would need to go through a complex exchange process, probably losing value in the transaction fees and exchange rates. This is exactly the problem we face in the blockchain world today. Each blockchain network operates as we call a silo, a self-contained ecosystem with its own rules, its own native cryptocurrency, and its own community of users and developers. Bitcoin has been around since 2009. Primarily focused on storing and transferring value. Ethereum launched in 2015 and revolutionized the space with smart contracts and decentralized applications. Then came Solana, offering the lightning-fast transaction perfect for high-frequency applications. Polygon emerged as a scaling solution for Ethereum, and Avalanche introduced the concept of subnets for specialized blockchain networks. Each of these networks is incredibly powerful in its own right, but here is the challenge. They can't talk to each other natively. A user holding asset on Ethereum can't directly send them to someone on Solana. A developer building an application on Polygon can't easily integrate functionality from Avalanche. This fragmentation creates several serious problems. First, there is the issue of liquidity fragmentation. When assets are locked within individual blockchain, it limits the overall efficiency of the entire decentralized finance ecosystem. Second, users face a terrible experience having to manage multiple wallets, multiple interfaces, and constantly having to move assets through centralized exchange just to participate in different networks. Third, developers end up duplicating efforts, building similar applications on different chains because they can't leverage code or functionality across ecosystem. We are moving towards a future where these blockchain silos become interconnected networks where assets and information can flow freely and securely between different chains, creating a truly interoperable decentralized ecosystem. Now that we understand the problem, let's talk about the solution. Cross-chain technology is fundamentally about breaking down the walls between different blockchain networks and enabling them to communicate and transfer value securely. Think of it as a building bridges between those isolated city-states we talked about earlier, allowing free movement of assets and information. First, we have wrapped assets. This is one of the most widely used approaches today. A wrapped asset is essentially a representation of a token from one blockchain that exists on another blockchain. The most famous example is wrapped Bitcoin or WBTC, which represent Bitcoin on Ethereum network. Here is how it works. When you want to use a Bitcoin or on Ethereum, your actual Bitcoin is locked in a secure vault on the Bitcoin network, and an equivalent amount of WBTC is minted on Ethereum. This WBTC can be used in Ethereum's DeFi ecosystem, traded, lent, or used as a collateral. When you want your Bitcoin back, you burn the WBTC and the original Bitcoin is released from the vault. The second approach is atomic swaps. These are peer-to-peer exchanges between different blockchains that don't require a trust intermediary. Atomic swaps use something called hash time locked contracts or HTLCs. The beauty of atomic swaps is that they are trustless, either both sides of the swaps complete successfully or neither does. There is no possibility of one party taking the assets and running. Third, we have bridge protocols. These are specialized smart contracts and infrastructure designed specifically to facilitate asset transfer between the chains. Bridges typically use either a lock and mint mechanism where assets are locked on one chain and equivalent wrapped tokens are minted on another, or burn and mint mechanism where tokens are burned on one chain and minted on another. Fourth, relay networks and validator set. These are a group of nodes or validators who monitors multiple blockchain networks simultaneously and verify transactions across them. They act as a communication layer, ensuring that when something happens on one chain, it's properly reflected on another chain. Each of these approaches has different trade-offs in terms of security, speed, cost, and decentralization. Before we go deeper into the cross-chain bridges, we need to understand Layer 2 solution because they play a crucial role in the cross-chain ecosystem. Many people confuse Layer 2 solution with the separate blockchains, but they are actually something quite different and quite clever. Let me explain what Layer 2 really means. Ethereum, which we call a Layer 1 or L1, is incredibly secure but has limitation in terms of transaction speed or cost, especially during periods of high network usage. Layer 2 solutions are built on top of Ethereum, processing transactions of the main chain but still deriving their security from Ethereum itself. It's like having express lanes on highways. The express lane is separate from the main highway, allowing faster travel, but it's still a part of the same road system and follows the same fundamental rules. There are several types of Layer 2 solutions. Optimistic rollups like Optimism and Arbitrum process transactions off-chain and assume they are valid unless someone challenges them. They are called optimistic because they optimistically assume transactions are honest. State channels allow participants to conduct multiple transactions off-chain and only settle the final state on-chain. ZK rollups uses zero-knowledge proofs to verify transactions, providing even stronger security guarantees. And then there are sidechains like Polygon, which are separate blockchains that connects to Ethereum through bridges. The key benefit of Layer 2 solution are dramatic. Transaction fees can be reduced by 90 to 99% compared to Layer 1. Transactions that might take minutes on Ethereum can be processed in seconds on Layer 2. And most importantly for our purposes, these Layer 2 solutions still benefit from Ethereum security, so you are not sacrificing security for speed. Now let's dive into the technical heart of cross-chain technology, bridge architecture. Understanding how bridges work is absolutely essential for building secure and efficient cross-chain applications. Let me walk you through the complete lifecycle of a cross-chain transfer. Imagine Alice wants to transfer 10 Ether from the Ethereum to Polygon to take advantage of lower transaction fees. Here is exactly what happens step by step. First, Alice connects her wallet and selects Ethereum as her source chain and Polygon as her destination chain. She specifies that she wants to transfer 10 ETH. When she clicks the transfer button, the platform initiates a locked transaction on the Ethereum network. This locked transaction calls a smart contract that securely holds Alice's 10 ETH. This isn't just any smart contracts, it's a carefully audited vault that uses multiple security mechanisms to ensure the funds can only be released under the proper conditions. Now, here is where it gets interesting. The moment Alice's ETH is locked on Ethereum, a network of validators that monitors both the Ethereum and Polygon chains detects this lock event. These validators are running specialized software that watches for specific events on both chains. They verify that yes, Alice's transaction is legitimate, yes, the correct amount was locked, and yes, it's safe to proceed with the next step. Once a sufficient number of validators have confirmed the locked and the platform typically requires multiple independent validators to agree before proceeding, which we call reaching the consensus. A mint transaction is triggered on the Polygon network. This mint transaction creates 10 wrapped ETH tokens on Polygon and sends them to Alice's wallet address. These wrapped tokens are backed one-to-one by the real ETH logged on Ethereum. Alice can now use her wrapped ETH on the Polygon for whatever she needs, providing liquidity to the decentralized exchange, participating in yield farming, or making payments. When she is ready to return to Ethereum, the process works in reverse. She initiates a burn transaction on Polygon, destroying her wrapped ETH. The validators detects this burn, verify it, reach consensus, and then trigger an unlock transaction on Ethereum that releases her original 10 ETH back to her wallet. Security is not just important in cross-chain development, it's absolute paramount. Cross-chain bridges have been target of some of the largest hack in cryptocurrency histories, with billions of dollars stolen due to security vulnerabilities. Let me start with the fundamental challenge. When you are moving assets between chains, you are essentially creating a new attack surface that doesn't exist on the single chain. On a single blockchain, you rely on the chain's consensus mechanism for security. But with cross-chain bridges, you are introducing additional point of potential failure. The first major security consideration is validator security. Remember those validators I mentioned who verify cross-chain transactions? They are the guardians of the bridge. If an attacker can compromise through the validators, they could potentially approve fraudulent transactions. For example, minting wrapped tokens on one chain without actually locking the corresponding asset on the another chain. First, it requires multiple independent validators to sign off on each transaction. We call this multi-signature or multi-sig approach. Second, validators are economically incentivized to act honestly through a staking mechanism where they put up a collateral that can be slashed or taken away if they behave maliciously. Smart contract vulnerabilities are the second major security concern. The bridge contracts themselves, the lock contracts, the mint contracts, the burn contracts, all needs to be absolutely bulletproof. A single bug in all these contracts can be catastrophic. The third consideration is what we call the trust model. Some bridges rely on a small set of validators that might be controlled by a single entity. We call these more centralized bridges. Others distribute validation across many independent parties. These are more decentralized bridges. Generally speaking, more decentralization bridges are more secure but might be slower and more expensive to operate. Time-locked and delay mechanisms are another important security feature. Many bridges implement mandatory delays for certain actions. For example, if someone tries to withdraw a large amount of assets, there might be a waiting period during which the community can review the transaction and halt it if something seems wrong. These delays can be annoying from the user experience perspective, but they are critical safety mechanisms. Finally, economic security through proper incentive design. Validators need to have more to lose by attacking the system than they could gain. If a validator has staked $1 million worth of assets, but the bridge only holds $100,000, that's good. The validator won't risk their $1 million stake for a $100,000 gain. As a developer, you need to understand these security principles because your application security depends on how you implement cross-chain functionality. Never assume a transfer is instant. Always verify that funds have actually arrived before crediting a user's account. Implement proper error handling for the failed transaction and always audit your code. Now let's talk about actually using the Xcan platform. This is where everything we have discussed comes together into a practical, usable development environment. There are story-driven tutorials that are wrapped into technical concepts in real-world scenarios. Instead of dry documentation, you are solving actual challenges. This shows you why concept matters and when to use them. There are interactive quizzes that test understanding throughout each module. You will debug code, predict transaction outcomes, and solve real scenarios. These checkpoints ensure you are building solid foundation before moving forward. After the module has been completed, you will earn NFT certificates minted on-chain. These are verifiable credentials proving your mastery. These NFTs become part of your developer portfolio and serve as a real credentials you can share with the blockchain community. So now, as I have completed all these modules, I can mint the certificate. As you become more comfortable with the basic cross-chain development, you will want to explore advanced patterns that make your application more robust, efficient, and user-friendly. Let me share some of the patterns and practices that professional cross-chain developers use. First, let's talk about the optimistic bridging with delayed finality. This is a pattern where you allow users to receive funds on destination chain before the source chain transaction has reached full finality. This sounds risky and it can be, but when implemented correctly with the proper safeguards, it dramatically improves the user experience. Here is how it works. When a user locks token on Ethereum, instead of making them wait for the full validator consensus process, you can credit their account on Polygon immediately but mark those funds as provisional. These funds can be withdrawn or transferred until the source transaction achieves full finality and validators confirm it. If something goes wrong with the source transaction, the provisional funds are simply revoked. This pattern is particularly useful for applications where user needs quick feedback like gaming or trading applications. Batching is another crucial advanced pattern. Instead of processing each cross-chain transfer individually, you batch multiple transfers together. This significantly reduces gas cost, but you are amortizing the cost of validator verification across multiple transactions. For example, instead of processing 10 separate transfers, each costing 0.05 ETH in gas, you might batch them into a single transaction costing 0.2 ETH total. Liquidity pool optimization is essential for production bridges. Instead of always using the lock and mint pattern, you can maintain liquidity pools on both chains. When a user wants to bridge tokens, they can receive tokens from the existing pool on the destination chain, which is much faster than waiting for new tokens to be minted. The locked tokens on the source chain replenish the source chain pool. This creates a liquidity as a service model where liquidity providers can earn fees by providing capital to these pools. Error handling and recovery mechanisms are often overlooked but absolutely critical. Cross-chain transaction can fail for many reasons: network congestion, validator timeout, gas price spike, nonce conflicts. Gas optimization strategies become increasingly important as your application scales. Every operation on Ethereum costs gas, and these costs add up quickly. Small optimization in your contract code can lead to 30 to 50% reduction in gas cost, which directly translate to better user experience and higher adoption. Cross-chain message passing is where things get really interesting. So far, we have mostly discussed transferring tokens, but you can also send arbitrary data and trigger complex logic across chains. For example, you might have lending protocol on Ethereum where collateral health is checked against price feeds from Chainlink oracles on Polygon. Or you might have a gaming application where your game states is maintained on a fast chain like Polygon, but high value item ownership is secured on Ethereum. Security patterns in advanced development require special attention. time locks for large transaction, multi-signature requirements for administrative functions, circuit breakers that automatically pause the system if unusual activity is detected, and rate limiting to prevent rapid-fire attacks. Let's step back from the technical details for a moment and look at how cross-chain technology is being used in production application today. Decentralized finance or DeFi is the largest and the most mature use case for cross-chain technology. Let's think about a user who has a Bitcoin but wants to participate in Ethereum's DeFi ecosystem. They can't use Bitcoin directly on Ethereum, so they use Bridge to convert their Bitcoin into a wrapped Bitcoin or WBTC. On Ethereum, this WBTC can be used as a collateral in lending protocols like Aave, providing as liquidity in decentralized exchanges like Uniswap or used in yield farming strategies. The user gets access to Ethereum's rich DeFi ecosystem while maintaining exposure to Bitcoin's value. Cross-chain lending protocols take this even further. Imagine a protocol where you can deposit collateral on Ethereum and borrow stablecoins on Polygon, or deposit NFTs on Ethereum as a collateral and borrow against them on Avalanche. This protocol uses cross-chain messaging to verify collateral on one chain while issuing loans on another. Multi-chain liquidity aggregation is solving a real problem in DeFi. Liquidity, the availability of assets for trading, is fragmented across different chains. An aggregator can find the best price for a token swap by checking prices across Ethereum, Polygon, Avalanche, and other chains simultaneously. When you want to swap token A for token B, the aggregator might find the best price on Arbitrum, automatically bridge your tokens there and execute the swap, and bridge it back to your preferred chain. All of this happen in what appears to the user as a single transaction. NFT bridging is emerging as a major use case. NFTs, or non-fungible tokens, represents unique digital assets like art, collectibles, or game items. The problem is that most NFTs are on Ethereum, where transaction fees are high. Cross-chain bridges allow NFT owners to move their NFTs to cheaper chains for trading or use in applications while still maintaining proof of ownership on Ethereum. Gaming applications particularly benefit from these. Games items can be traded frequently on a fast, cheap chain, but their ownership records are secured on Ethereum. Speaking of gaming, cross-chain gaming is one of the most exciting emerging use cases. Imagine a game where your character's state is stored on Polygon for fast, frequent updates, but rare items and achievements are minted as NFTs on Ethereum for security and permanence. Or a game that allows players from different blockchain ecosystems to play together in the same virtual world. Supply chain tracking is an enterprise use case that is gaining traction. A product might be manufactured and registered on one blockchain, transferred through distributors tracked on another blockchain, and finally sold to customers with records on the third blockchain. Cross-chain bridges ensure that all these parties in the supply chain have a consistent view of the product's journey, regardless of which blockchain network they are using. Decentralized identity is another promising area. Your identity credentials might be stored on one blockchain, your professional certificates on another, and your transaction history on the third. Cross-chain technology allows applications to verify your complete identity by pulling the data from multiple chains. Even with the best planning and coding, things will go wrong. Cross-chain development introduces unique challenges that can be frustrating to debug because you are dealing with the multiple blockchains, multiple transactions, and multiple potential points of failure. Let me share the systematic approach to debugging that will save your countless hours of frustration. The first step in debugging any cross-chain issue is to identify where in the process the failure occurred. Break down the cross-chain transfer into stages. The source chain transaction, the validator detection phase, the validator consensus phase, and destination chain transaction. Transaction monitoring tools let you see the status of each cross-chain transfer in real time. You will see when a locked transaction is submitted to Ethereum, when it is confirmed, and when validators detect it, when the consensus is reached, when the mint transaction is initiated on Polygon, and when it is finally confirmed. If something goes wrong at any stage, you will know exactly where to focus your debugging efforts. Let me walk you through some of the most frequent issues. Network selection errors are incredibly common. A user approves tokens on the wrong network and then wonders why their transaction won't go through. The fix is simple once you identify it. Make sure your user interface clearly shows which network the user is connected to and provides clear instruction for switching networks. Allowance and approval problems trip up many developers. Remember, before a smart contract can transfer tokens on behalf of a user, the user must approve that contract to spend their tokens. This approval is chain specific and token specific. If a user approved tokens on Ethereum but your contract is trying to spend them on Polygon, it will fail. Always check token allowance before attempting transfer and provide clear error messages to user when the approval are needed. Gas estimation failures happen when the network condition change between when you estimate gas and when you submit the transaction. Stuck transaction with nonce conflicts are frustrating. Every Ethereum account has a nonce transaction counter, and transaction must be processed in nonce order. If a transaction with a nonce 5 gets stuck, all subsequent transactions are blocked. Validator delays can occur during the period of network congestion when validators are processing a high volume of cross-chain transfers. If a validator are taking too long, you might need to increase validator incentives or wait for the queue to clear. Block reorganizations or reorgs are a subtle but important issues. Sometimes, especially on chains with shorter block times, a block that was thought to be confirmed gets reorganized out of the chain. On Ethereum, 12 confirmation is generally considered safe, while on Polygon you might wait for 100 confirmations. Testnet versus mainnet difference can cause unexpected behavior. Testnets often have different block times, different gas price dynamics, and sometimes even different consensus rules than mainnets. Lastly, build something. The best way to learn is by doing. Start with a simple project, maybe a basic token bridge or a cross-chain voting application. Don't worry about building something revolutionary right away. Focus on understanding the fundamentals, and complexity will come naturally as you progress. And do not forget to submit your project on Xcan Platform. Here is the chance to get your project featured on Xcan. Thank you so much for joining me on this journey through cross-chain development with the Xcan Platform. Happy building!